Okay, good afternoon, everyone, and good night to Kateryna in wherever she is now. So I believe that in a long history of CCPO, this is the first time that we have a speaker from Ukraine. Kateryna, I met her more than 8 years ago when I met her and her husband, who is also a scientist in China, doing a summer training workshop. And then we met again earlier this year at the EGU meeting and in Vienna. And I was quite amazed, not only of the research that she's doing, but also all this outreach with education and STEM research and mathematics for children and so many other activities despite the terrible condition in Ukraine, the war that is going on. A little bit about the background. Kateryna has a PhD in physics and mathematics and numerical modeling of hydrodynamics and oceanographic problems. She has been a senior scientist at the Institute of Mathematical Science of the National Academy of Science of Ukraine. She also got many different awards, like the winner of the Real Award for Women in Science. She's also involved in some other STEM programs to encourage girls to choose mathematics and tech-related studies. And today she's going to tell us about internal waves. And I have to mention that this seminar is supported by the Center for Coastal Physical Oceanography and also ICAR, the Institute for Coastal Adaptation and Resilience. So I think that we couldn't choose a better candidate for resilience to have to do science under war conditions. So maybe she'll tell us also a little bit about these too. Okay, go ahead. Thank you very much for coming.
Thank you very much, Tal, for introduction and for this possibility. It's a great honor for me to present my research and maybe possibility to talk about situation in Ukraine and about Ukraine. Thank you. So my name is Kateryna Terletska, and I'm a researcher from Ukraine, a country that now living through a war. And the question of our future, maybe, and the direction of our history, maybe, partially being decided in Ukraine. It's my opinion, but so please, next slide. And that's why I like to begin today's talk with a moment from the past, a great battle that once shaped the destiny of the ancient world, and that is the Battle of Actium. It's 31 BC, and that was not only a military confrontation between Octavian and the alliance of Mark Antony and Cleopatra. It was a turning point that determined the future of Rome itself and maybe all our European history. And it's interestingly that natural phenomena I study, internal waves, maybe played a silent but decisive role in this historic event. So this was a confrontation between Octavian on one side and Mark Antony and Cleopatra on the other side. And as we could see, Octavian commanded about 400 ships and 80,000 soldiers. And while Antony and Cleopatra had slightly more ships, 500. And you can see the map just in the center. But in spite of more ships and more powerful fleet, Antony and Cleopatra defeat in this battle. So next slide. Antony forces found themselves at a strange disadvantage. Ancient sources tell us that Antony remained motionless for 3 hours at the exit of the Gulf. Instead of breaking through Octavian's lines with the force, his ship failed. They failed to gain speed, and his fleet was eventually overwhelmed. And yes, it was a crucial crucial event, and was crucial for Antony and Cleopatra. And yes, Octavian's became master and of Rome Empire. And what we have from this history, for example, Pliny the Elder, he wrote that it was a small fish called remora that could stop a vessel by clinging to its hull. And that was the myth, of course. And now some explanation of this situation, this phenomena, is because of internal waves, and so-called dead water was the reason that Antony forces could not move. And next slide. And the reason of this is a dead water. We will move it on the next slide, but no, please return back, thank you. But I just remind what is the internal waves. So internal waves, that the waves, they emerge when we have layers with a different density. It's usually in the ocean or even in the basin like lake, because upper layer is always have a temperature. For example, in a summer it's more warm water and more cold water in the deeper part of the basin, and on the interface of these two layers could travel internal waves. So next slide. Of course, it could occur not only due to a temperature, also due to a salinity gradient, and the phenomena that was described by Plinius the Elder, called dead water. And he described also that ships would suddenly stop, like they held back by unseen hand, and couldn't move further. And we could see that now it explained also by internal waves, because when the ship tend to move, and they can and the velocity of the ship, they are close to velocity of internal waves that generated also by these ships. So the energy of movement, it's not enough to move, and it's also dissipated to overwhelm this internal wave that is unseen. So the next slide. And it's not only one legend that could be connected with internal waves. Another myths from Homer Odyssey, it's Scylla and Charybda. And Scylla was imagined as a terrifying rock creature that attacks sailors. And Homer said that it was deadly whirlpool that also sucking the ship into the sea. And also now we have explanation of maybe this legend with the use of internal waves, because in this very narrow strait, mixing the layers and water from different seas, from different salinity and other characteristics. So, and that's why also in this strait could occur very strong internal waves, and we could see it also on the on this on this velocity field from the strait. Next one. And one more legend. It's a Loch Ness monster. It's also a very famous legend, and this creature is living in Loch Ness Lake, and it's located in a great glen, and it looks like basin for laboratory basin. It's very deep, and it's very steep, have very steep slopes. And some people said that they could see different humps on the surface, or something that moves like a ship. And there was our explanation. We made a modeling in Loch Ness Lake, so you could see the bathymetry of Loch Ness Lake here. And we also did modeling of very strong internal bore. So you could see here it also was measured. It was known maybe 50 or 60 years before that in Loch Ness exist very strong internal seiches, and this nonlinear bore that travels from one side of the lake to another side, and also this bore interacts with sides of the lake. And we did a modeling and also obtained the situation when we could see the ship waves, and the source of these ship waves is strong internal waves. But it's our modeling, but also there are lots of other explanation, also with the use of internal waves of different phenomena that could be explained or by some person like Loch Ness monster. Next slide. Thousands of years, it was unknown and strange phenomena, and nobody knows what is hiding under the water surface. And the first person who observed internal waves was Benjamin Franklin. He was traveling from Madeira, and there was the oil lamp. And here is some information what he observed. That yes, the surface of the oil was very calm, but on the interface of oil and water, we could observe huge breaking waves. So it was the first observation of internal waves. Next slide. And first ever measurement of internal waves was produced by scientists on ship Fram. It was conducted during polar expedition, and with Fridtjof Nansen. And basically, first observation was done by him, and you could see this variation of salinity and density, and it was on Norwegian fjord, where we have fresh water on the top and salty water on the deeper layers. Next slide. And Fridtjof Nansen said that the knowledge of the exact nature and causes of these waves and their movements would be, in our opinion, be of signal importance of oceanography. And as far as we can see, it's one of its greatest problems that most urgently calls for solutions. So the era of study internal waves, it's about 100 and several decades. So it's very young science about internal waves. So the next slide. And observation of internal waves begins at the middle of the 20th century. And we could see here the maps where internal waves were observed. But now the situation changed with AI and with lots of data. Of course, this map changed dramatically. Internal waves could be observed everywhere in the ocean. And also, most impressive, the amplitudes of internal waves. So the next slide. The largest internal waves that observed in a world ocean. So you could see also quite old map, but we could see that internal waves could reach hundreds of meters. And one of the greatest internal waves that was observed had the amplitude of 240 meters. So these huge waves, they are generated in Luzon Strait, and they are traveling through the South China Sea, and they could break and they could mix the ocean, mix the layer, transport oxygen, transport nitrogen, and internal waves, they are very important in ocean mixing. And lots of study we did before was about mixing of internal waves breaking, and so on. But for last maybe 4 or 5 years, the most of the interest concentrated on the polar region, because polar regions are very important in global climate. And understanding of what happens on the polar region is crucially important for understanding of global climate system. So next one. And for years, our team involved in 2 projects. First, it's Polaris, it's a Horizon project, and another is Ocean Ice. And my role in this project is to understand the role of internal waves in Arctic and Antarctic, because they also play a very important role in mixing and transporting heat, salt, and nutrients beneath the ice. And ice reduces wind-wave interaction, and it leads to weaker internal wave climate. But in summer, ice cover thickening and shrinking, and in this situation, internal waves become more energetic, and also their interaction with keels, with the ice cover, and understanding the role and how internal waves could mix the layers, and could they will they increase melting or no, and how they mix the layers beneath the ice. that was quite important question, and we try to give, maybe not to give the answer, but to do some research on this topic. So next one. So what we have to know about to make a modeling? Ice geometry, we have to know what is the depth, what is the characteristic of keels, ice keels, their width, their slope, their distribution. We have to know stratification also from data, and wave properties. Amplitude, wavelengths, and the shape of the wave in the Arctic region. And with the last, with the wave properties, we had very few data, but mostly lots of data we have now about ice and about keels geometry and fine structure of ice, and that's why it was very important to understand how the internal waves interacts with the ice keels, with this fine structure of the ice, and that was the topic of our research. Next slide. And as already mentioned about the tools I use in my research, it's three-dimensional, non-hydrostatic, free surface POM model. So it's non-hydrostatic extension of the POM model, and our team did it 13 years ago. We did this modification. So, and this is an equation of this model. And for a large-scale problem, we use Smagorinsky turbulence model. And I didn't put lots of information about the model. So maybe if you have some question, I could reply and discuss just the model, but next slide. So what's the role of ice keel on the internal wave dynamic? So as we could see on this diagram, on this scheme, interaction of internal solitary wave with this age of the ice and with these keels, it leads to destabilization of internal solitary wave. It could break beneath the ice keel, and they could transfer the energy on a secondary wave, and then the secondary wave also interacts with each other, and so the internal solitary wave with some parameters could disappear or break in when it passes under the ice. So next slide. And when we came to this problem, how to treat with the ice, what to do, how to do modeling, we just use our previous series of work. We did lots of modeling, interaction of internal solitary waves with the bottom step. And we did a lot of research because POM model give us possibility to deal with this very complicated shape. Yes, because the step we have problem always in lots of model, we have problem on this corner, on this square corner, but here we could skip this problem. And we did a lot of research modeling of internal wave over first mode with a step, with the second mode, with some very crucial obstacles on the bottom. And we used some results from this paper. It was paper 2013 in Physics of Fluids. And that was the research interaction of waves of elevation and depression with the bottom step. We have a lots of run of different amplitudes of different geometry and different parameters. Next slide. And yes, here are some beautiful examples of interaction of internal waves with a step. For some geometry, for some parameters, we could observe very beautiful Kelvin-Helmholtz instability if the amplitude was too large. And on the lower panel, you could see also formation of internal boluses on the step and jets for wave of depression and this bolus for wave of elevation. Next slide. And what the main result of this work, we make a classification of different regimes of waves, internal waves with a step, and also calculated energy lost. So because due to interaction of internal waves with a step, we lost a lot of energy, waves are dissipated, and for some parameters we have this maximum dissipation and energy lost, about 50% of all energy of the wave are dissipated on the bottom step in strong interaction regime. And here some regime that is a weak interaction, when the energy almost the same, so waves are not losing their energy during the interaction, and maximum strong interaction, and also transmissional regime and reflection. So when the step is very high and the wave simply reflects from this step. And we use some results and some methodics we use for this research. We also did it, next slide, for ice cover. So we just turn our numerical Bayesian. Yes, we also did some comparison with the free surface and with a rigid lid. And we understand that for some range of amplitudes of internal wave, it could be appropriate approximation. And also we make lots of run just with a step, just with a flat ice cover. And also we did a lots of run with ice keel. This is B, yeah. Runs also to understand how the wave interacts with this ice keel and what is the dependence of energy loss when we change some distance between ice keels and when we change their amplitude. Next slide. Yes, and also we did the same classification, but just for turned laboratory tank. And we also compare the results of runs for these two cases, and we could see that it's almost the same. Next one. And the next problem was to understand that the real ice keel geometry, because all these problems, all this calculation before, they have mostly just theoretical interest, because we need to be more on the data, on the real ice keel. Next slide. And also we collect different data, different information about ice kill from Arctic and Antarctic Ocean. Basically, in Antarctic Ocean, there are very few data. And also we have some geometry and some data about ice kill in Antarctic Ocean. So it's maximum of the ice draft, it's about 16 meters. And the next slide. And in Arctic Ocean, we have an amazing project, Mosaic expedition with lots of data. It was conducted in 2019-2020. And it contains lots of data from remotely operated vehicle. And I think we have more than 30 different data sets for ice depths, ice, and next slide. And not only this project, also we have some other projects and information from some other projects. And what we could conclude here, the table with the measurements for Arctic sea ice and Antarctic sea ice. And we know that Antarctic ridges are generally flatter than Arctic ridges. And the dimensions of Antarctic ridges are significantly less than those of Arctic regions. Next slide. And compare and return to Mosaic project. It contained such data sets of ice cover. And what we did, we analyzed mostly all of them. And next slide. And we cut them, and for this cross section, for each cross section, we apply continuous wavelet transform and try to estimate the dominant spatial scales. Because for us, it's very important to understand what the spatial scales are for basically for Arctic and Antarctic. Next slide. And what was the conclusion? That we found two dominant scale. So first one was about 40 meters, and this scale is linked to smaller ice keels. So they're usually quasi-isotropic. They are just like these cones with usually depths about 10s or 15 meters. And another, it's large scale ridges with a dominant scale about 100 meters. And it's usually anisotropic. And basically, we choose for our for calculation these large scale ridges to understand and to investigate how this fine structure influence internal waves. Next slide. So yes, here is one of the cross section of the ice cover, and we also approximated to Visuria function with some these peaks inside. So the envelope of this red curve is a Visuria function with different numbers of small keels inside this envelope. And the blue one, it's a little bit smoothed but realistic ice cover. Next slide. So yes, so here is a numerical configuration. One is more theoretical with Visoria function with a different number of Keels, and another option when we make modeling with a realistic ice keel formation, ice keel ridges. Next one. Yes, and here is also the example with a smooth hill with like one keel and the envelope with the 7 keels, how it looks like, and the envelope with the 13 keels. And so we did a lots of run with the different amplitudes to test how this fine structure imply on energy lost of the internal wave that pass underneath this ice keel. Next slide. Yeah, and here is the results of modeling. We could see the internal waves quite small comparatively to ice keel structure, and it interacts with the 1 hill and with 7 and with 13 keels. And we could see that, next slide, that on a case with lots of keels, we also could see the formation of reflected waves and formation of the second mode internal solitary waves, and they also then interacts with each other. Yeah, and mix the pycnocline. Next one. And some results when we have internal wave that interacts with ice keels formation of the same order. That here is a wave have a much bigger wavelengths, and it interacts with these two cases with a realistic ice keel and with this more theoretical one with they described with Visoria function and vorticity. Next one. And we could see the formation of vortices that occurs due to this keels, this formation, and we could see the vortices just inside between two keels, and also these patterns was observed in experiments. I just missed here the author. It was the paper CAR, and there was the research of interaction of internal waves with the corrugated bottom. Of course, they are of a different lengths and different scales, but also we could see the formation of vortices between this corrugation, as in our research, in our modeling, and in laboratory experiment. So next one. And we also calculate energy lost and try to understand how the energy lost depends on number of keels and the ratio between wave amplitude and the distance and the all length of envelope. So we could see that the highest dissipation occur when we have 13 keels, and when wavelengths is much larger than the keel envelope, energy losses is almost constant, so it doesn't matter what is the ratio, but it turns to be constant. And however, when the keel envelope exceed the wavelengths, and turbulence and wave breaking in this case intensify dramatically and increasing dissipation. Next one. So the all conclusion and finding geometry is important. Keel shape, slope, and its form, it's dominate over just keel number. So it's important. Mixing vortices at the keel edge disrupt the picnic line and enhancing turbulence. Energy lost. So nearly constant energy lost when wavelength is much larger than length of envelope, and rise sharply when length of envelope is much bigger than wavelengths. And multiple keels also generate high mode waves, intensifying energy transfer to turbulence. So next one. And beyond. So that was the project that we did. And all our team in Institute, in National Academy, involved in lots of different projects. And how we survive in war. Please, next slide. So some numbers, maybe it would be interesting that during the war, it was a report, I think it was the last year, about 1,400 buildings was damaged or totally destroyed. So about 640 pieces of research equipment was damaged. Among them, lots of very important things in Kharkiv. So some telescopes, some very important nuclear objects were destroyed, and there is some estimation of funds that need to restore public research infrastructure. And it's officially about 12% of Ukrainian scientists and university teachers forced to emigrate. But I'm not sure that it's only official one, but I thought that numbers are much greater. Next one. And about 30% of Ukrainian scientists forced to work remotely, and about 1,500 now volunteered, and they are in military, they are in army. 53 countries, they're hosting displayed scientists from National Academy of Science. Yeah, and some budget, it's dropped, but due to donors, due to support, now in Ukraine we have lots of possibilities, lots of grants. And the main problem now, not lack of the money, but lack of the people. Next one. And yeah, it's just last night. I'm not in Ukraine. I'm in Austria, but I think almost all nights looks like this one. So it's air threats and movement of drones, of rockets, almost every night in Ukraine. So you could imagine what people in Ukraine feel, how we survive in such when you could not sleep, for example, for 1 week, for 2 weeks. Yeah. So please, next slide. Yeah, but anyway, we try to be resilient. We try to survive. And as I mentioned, we have lots of different projects. And recently, we opened Museum of Mathematics in Kiev. And now we plan to make a traveling exhibition throughout of the Ukraine, to bring these exhibits to small cities, to other regions. of Ukraine, and you could see this amazing space in Kiev. And for me, it was very important because we prepare and we start this project before the full invasion, and prepare and buy and discuss lots of exhibits. And then project was frozen for 2 years. And finally, we opened it on the May 1st. It was 4 or 5 months ago. Next slide. Yes, and for me, it's very important because I teach teachers. So every weekend for 2 days, teachers from all over the Ukraine, they visited Kiev, and we are doing with them lots of hands-on activities. So because for us, we have this Soviet heritage, and our mathematics of high level is still very strong, but in general, for average pupil, for average kid, this mathematics is it's not interesting, it's boring. And what we have to do, we have to do some tricks to show them bright and vivid exhibits. And so maybe these days it's my main activity and mission, just to teach teachers, to give them some new methodics, and then they could use it in their schools. Next slide. Yeah, so for these 3 months, over 1,000 teachers, they completed training. So they came, and they for 1 or 2 days are in museum. For all days we did different training, and yes, almost 1,000 already visited Kuboet and this training. So next slide. I'm finished, and thank you for your patience, for your attention, because I'm a bit tired, because I have almost yes 10 o'clock. Yes, thank you so much.